Welcome everyone to another amazing live stream here with this ULX3S previous icebreaker, now this larger board here of FPGA open source open hardware goodness. And yesterday we were working on our SDRAM controller here for this on this revision anyway, 64 megabyte 512 mbit. Your mileage may vary, you probably get a crowd supply, right? So if it comes to crowd supply, they probably have a smaller one, but anyway. And yesterday we had quite some bit glitching going on there, and as seen here on the stream, we finally not only have here non-randomly, do I also show this, non-randomly flickering bits, but we also pass the full of our own mem test. Some mistakes were made that I want to share here with you as usual. Also the mem test here as running live here on this currently 41.667 megahertz clocked RISC-V core. Running quite a while, the memory clocked with 80 to 84, 83. Also as seen here, 83.33 megahertz. And so yesterday, if you want to see the details, probably previous video, while the memory test is running, probably let's check here some comments in the meantime. Mistakes were made in terms of, and we passed again, and this takes so long. It's not only writing most of the memory, 64 megabyte, also no cache, right? So this is uncached and so on a probably less than 4 clocks per instruction, or more clocks per instruction RISC-V core. Anyway, so yesterday we took a look here on those timings, and I had them mostly right. We just had some bit garbage there, sometimes more, sometimes less, and debugging this, tracking this down, as you can probably imagine, took quite some pain, took a couple of more hours, because why not? And long story short, the first mistake was here in my ready signal generation. In yesterday's live stream, I had here, theoretically can also show you this of somewhere of earlier commit, like whatever, mostly working as stream controller, something of does get this work, or maybe not. Somehow this outputs quite a bit, and I have a feeling that is not the greatest fan of Git. Anyway, in yesterday's state machine stuff, we have the state machine of different row, column addressing and command and so on. And I generated the ready signal here previously always on the second cycle after the read, or it doesn't really matter. I also tried a couple of more variants. It turned out I made here one super large mistake of this state machine takes 16 clocks. So we have here like 1, 2, 3, 4, 5, really many clocks. B, C, D, F. And so we have the command like here start, then command, then on read like cast latency. Actually we have here command, we have here address like row and column, and then eventually like here read, and then we are ready like something like here or something. And here we generated the ready signal here for our RISC-V core of hey, we are done and the address is valid. And actually nobody mentions this, so much to maybe nobody of you previously noticed this, but our RISC-V core could issue here in 2 clock cycles. So our RISC-V core is running with half the clock. So at any point in time, like here or here or here, the RISC-V core could issue this read like our C program as compiled to assembly and machine language and then to the instruction set architecture. In the bits, they decide on this clock or any other clock, hey, I need some memory. And the state machine previously, as of yesterday, would say, yo, we are ready, which is like, yeah, we have not even done it yet, right? So much to how do Intel like amazing bugs occur, like, yeah. So I solved this, so certainly we should only generate this ready signal after we actually issued the command. You can implement this in various ways. I've chosen here for now, I've also, what you see probably that if you compare this to yesterday, the code is actually quite a bit more cleaned up. And I've chosen to generate here some active cycle, here some registered active cycle, A cycle, and we set this on the start of this state machine to, hey, we are active. And we have 2 bits for this. We have output enable for read and write enable for write. And because there's another catch, initially I set this on start always to 1, which also resulted in some, I think, random garbage. Yes, so this also resulted in some random garbage, although less, because the next thing is also we should not have an active cycle if we do not even head in command. So otherwise, if we always set this to 1, we don't issue in command. We are pre-charging or auto-refreshing the SDRAM. And so we're not running a command. The RISC-V core says, hey, I need some memory. And we say, yo, here it is. And yeah, we were idle, right? So much to always find little details here live on this channel. So with this cycling here of active cycle, you could also implement this again in many other various ways. This already solved most of the issue, unfortunately not all. We also had another tiny little synco here in terms of writing. So after another hour of guru meditation of all this thinking about each state, what could possibly go wrong, and probably maybe you draw some diagrams and do some formal verification. I heard that is recommended in the industry, especially also Intel should probably do that. But the next thing is that the write, so we want to burst, right? So I said yesterday that this performance was not optimal, and because again this, now I just deleted this, which also probably can here, we have so much to redo. We have this 16-state machine for working with SDRAM addressing and super slow. So certainly for this 16-bit, yesterday's video also detailed 16-bit memory here on this and 32-bit microprocessor. So of course we do not want to waste 32 cycles, okay, divided by 2, but still 16 cycles. All this stuff is already slow enough. We should certainly optimize the heck out of it and make it as fast as possible. So I said already yesterday, ideally we should burst, which is the original code I based upon did not even dare to implement, because then we have read here and the first data coming out here and the second data coming out there, and then we are basically done here. And this was pretty easy, and in theory I showed you this here. Burst read here, just issue the read, and then either castle latency 2 or 3, the data comes out. Fair enough. We still had some random bit flipping, and after lots of guru meditation, only with all these improvements, mostly with the higher word of, we have 2 16-bit words, and it turned out I had this write here wrong for the data output for the write, because I had this here coded on, as you have seen yesterday, I had this state command read write, because thinking somehow the read write is in the same cycle, but that was a strategic fail and mistake, because the write, as probably maybe write A without a pre-charge, where's a good example? The write is instant, so the write has no cache latency. It has it internally, certainly, but you write the data exactly. Here is this example, for example, read with write interval, burst length 4, doesn't really matter too much here, but interesting stuff. So you see here in this T6 in this diagram, here is the start of a write. So here's read A, no operation stuff of bus busy, also cache latency until the first data comes out, and then write. And this write here is directly fetching in this data from the shared I/O bus. And so yeah, this was off. This also was only affecting half in this burst anyway, because the original code generated the signal anyway for all of the state machine addressing cycle of, actually we don't have it here right now, but of all the RAS, CAS and so on, raw and column addressing. And so yeah, so this was a simple fix of changing this to state command continued. This is the first state here after we issue the write. We need to compare this here to command. You see a command first, start, continued, read, write, or read. And so this is state 0, state 1, and then start plus RAS CAS delay and then CAS latency. This is only for read, and for write, this continued state is here this state to base upon. So you see here, this is write enable, the state command continued with command write for the command of the state machine running. And so yeah, the fix for the other half of our burst cycle for writing was as simple as actual fixing here the correct state in the state machine. And that was mostly it. 2 hours or so of open hardware guru meditation here, kinda sort of live on YouTube. This was, however, still not all. You would think after all those pain this would finally work. No, we still had random, not many, but some random bit flips, and this were a total pain. And they somehow, I've not really found this. So the reason this is running, you see this is running right now stable. Also again a memory test, because memory test. This is now stable. After another hour of guru meditation, it's clear to me this is timing related. I am just not sure why. What is really strange, so the only way I fixed this is actually I lowered the clock a little bit and now it's stable. And somehow this, however, is not like the memory could run at this frequency, because what is super strange, I tested this. Maybe you have an idea. So here we have this state machine of clocking in the data from the SDRAM memory. Here's a read command and here's a burst read command, and reading in the data. And I tested this already yesterday. I tested this because yesterday we had also all this bit fiddling there that was randomly wrong. I tested already yesterday with ±1 that this data is correctly latched out from the memory controller from the integrated circuit at the right clock. So ±1 results in mostly 0. So far so good. So this clock cycle that we log on is correct. And what is super strange, when we run this previously, I think yesterday probably I've run this 90 or 100 megahertz, probably 90. And when I change one of those assignments here, this non-blocking statement of copying, transferring the data here into this register of flip-flops, if I have only one of those 0, it works. The other half works stable. I can run memory test for hours. It's stable. So I mean, like this, only like not loading this here in. Oops, I also hate this automatic Emacs mode. So either this stable, perfect. Memory test with this bits, no problem. Other half here also. So I have like 0 ideas. So I experimented with making this data out register. Right now it's 32-bit. I experimented for an hour of making this two 16-bit registers, of having this buffered inside here in a register and transferring it here in another buffer, like double buffering it. Also didn't help. I have no idea why inside the state machine, this is that timing rate. This is also the reason why I've rewritten this earlier yesterday. This was open coded with ifs, if this state, then if that, then the other state. This is also why I tried to optimize this here. I even optimized this signal generation of this one here, of not depending on write enable, thinking like maybe conditioning this on write enable has another latency of a couple of nanoseconds there, of one more flip-flop on the way. This also didn't help, so I experimented for 1 hour with optimizing this. Also super strange because next PNR is giving this memory clock. Next PNR correctly knows it's connected to our PLL with, for example, 90 megahertz or 100 megahertz, and its next PNR is giving this this signal a maximum frequency of 180 megahertz. Maybe we even, not sure, now we have scrolled back so much from the memory test. Maybe we even have it here apparently in the scroll back. So this should be global clock. Where is our maximum frequency for clock? Probably this one. It should be this one, and as you see, probably this is after my optimization. I think before it was 180 something megahertz, so optimizing this maybe a little bit improved it to nearly 200 megahertz. So I have no idea why next PNR says, hey, this global net SDRAM clock here passes at 83 and is calculated to be good at S198.65. Maybe as we are still getting started here and learning all the guru meditation here live with you on YouTube, maybe if I feel another day, I maybe ping Claire on so, or chat with some other people. If you have any ideas, what I would totally understand, what puzzles me the most with this is, I would totally understand if this is timing sensitive and it never works. Like even if we assign a 0 here, it doesn't work. But this way, the least significant bit, the bottom half, works reliably, no problem for hours. So this is what puzzles me. So I have no idea what kind of load on the signal of potentially, I don't know, potentially more load on those memory lines of signal degrading a little bit more. I have no idea. If you have an idea, let me know. Maybe again, I yesterday speculated that outputting here this command bits here of SD command address stuff directly here with this assignments with what is the term for that, with not sequential, but you know what I mean, logic, then maybe this results in a signal slightly couple of phase degree out of sync. Maybe now that we learned all the details and have this in theory working, also with a tiny little decrease, this is why we decrease this as a frequency here to 83 instead of 90. So just 83, this is right now exactly the threshold of this becoming glitchy. Certainly not the most amazing way to run this, just at the edge of being glitchy. But anyway, so if you have any ideas of this load or of this timing here, let me know, because it's certainly super curious. But for me, this is good enough now. After 2 days of 20% fun time here at Xrcode between our don't delay, try exact scan, paperless scan office software today, I do not spend more time with this today. What I will probably do is rewrite it completely with only sequential logic and not, was it discrete logic? Anyway, earlier, somehow always for YouTube, start to forget this term. Anyway, I'm totally thrilled that this, despite this tiny little things, I optimized this a little bit more. So what yesterday for stability, I had this ready because, again, yesterday this was still more off by 1-2 clocks here and there. So this is even this signal stability here of latching in this SD I/O data doesn't change if we signal the RISC-V core later that we are done. I experimented with this and I determined now that everything, as far as I can see, is spot on and hopefully perfect, at least until 83.33 or some megahertz. We can directly, after latching this in this clock, signal the RISC-V Pico SoC, hey, we are ready. Stable, no problem. I also, because we can't make this faster with clock frequency right now for whatever clocking reasons here, that I reduced the cache latency to 2, so at least a little bit more performance, like 1 cycle better performance, that the read data comes out, and we already are bursting, so this avoids already the massive latency of setting up another command. Next steps, of course, in terms of, probably the next most convenient thing is getting the SD card implemented here for real fun of playing real games and stuff. And then, of course, the low-hanging fruits of porting Doom and having other kind of fun, or Pac-Man Tetris. And then, of course, optimizing the heck out of it. Speaking about optimizing the heck out of it, some more ideas. I think this state machine is overly pessimistic. As I said, it's running in 16 states here, somewhere of here, last state 0 to 15. I think this is suboptimal because we inherited this design, and again, most likely I will redo it completely. I cleaned it up already enormously, in my opinion. I made it bursting and 32-bit outputting and inputting. And if I rewrite this, because if we are idle right now, we are wasting always 16 cycles. So imagine our RISC-V core wants some data. We are cycling there in this idle states of auto-refreshing. And so we, worst case, need to wait 15 cycles until we can issue a command. That is certainly bloody inefficient. And I don't think we need to do this. So I think we can just run here auto-refresh, idle and auto-prefresh and whatever. And instantly, like without, if we are not issuing a command already, which in our Pico SoC example will not happen anyway, like 2 commands at a time is not possible. So in my opinion, we can avoid another average. If we take the average, worst case 15, best, so this is an average of 15, half of 15, so an average of 7.5, well, memory clock cycles, so RISC-V system bus cycles, half of this. But so this can be optimized, the state machine stuff, issuing the command instantly, idling more, basically idling and auto-refreshing more, if more efficient, in only 1 or 2 interleaving cycles there instead of 16, in my opinion. Judging you from this, because as you see from this diagram, I think this should be possible, as we have here somewhere the diagram for interrupting a read, maybe like this one, read to write latency. So you see we can here directly transition from read A to write B in like 1, 2, 3, 4, 5. So yeah, in my opinion, this should work, improving the performance, in probably easily doubling the performance. And then the next thing, of course, implementing an L1 cache, because performance. Certainly this is what you want in any case for your CPU, because as you probably seen from other YouTubers, if you switch off the cache in a modern Ryzen, or even half vintage Athlon or something, or not to mention 486, to get down to XT speeds, even all of those modern monster processors without cache, they are bloody inefficient and slow as an Pentium 100 or something. So certainly a nice exercise for another weekend, maybe later this year. First, we implement more features now that we have 64 megabyte of freaking SDRAM at our fingertips here for testing and memory testing. So yeah, decompressing JPEGs, MP3 audio. Certainly, if we really want to real-time decompress MP3 audio on this RISC-V, I think this probably was 60 to 100 megahertz, 486 or something. Certainly, we need to optimize the heck out of this if we want to have this playing MP3 in real time. Maybe also with another more RISC-V core. But the good thing is we have this Verilog modules, and we can in the future mix and match this, hopefully. So yeah, next SD card, another maybe in a week. Also next, some more different videos of not to have you only an FPGA overload. I hope you learned something from all those details. This is basically everything that I right now remember from all this guru meditation, except some small stuff like previously I had this data write mask here inverted because yesterday I said this also took me in 40 minutes to find. Now I'm, just for the sake of it, I'm inverting this already because it's named DQM. So I invert this, I negate this here in DQM, here in the Pico SoC, here just a little bit for readability. I also have done this for performance maximizations. Not to do this here, I'm not really sure if this helps a cycle or something, but all the little bit stuff of fine-tuning, readability, of perfecting this. So yeah, another memory test cycle successfully finished. I slightly wonder, we probably should be in quad DDR mode for the SPI. Let's toggle also continuous read mode and do that again. This theoretically maybe improves because we are running the RISC-V code from the SPI. Probably we can also drastically, for fun fact, maybe we have more significant fun also with just-in-time compilation because this mem test would certainly also be way faster if we would not running this from the quad SPI continuous read high performance SPI flash previous videos. But if we would run this from our SRAM, we still have 128K of basically SRAM single cycle instantiated FPGA memory. But yeah, even you see quad SPI continuous read mode running memory test here stable. I hope you learned something and enjoyed this. Give it a thumbs up if you have. Leave comments below, especially if you have something for the timing glitch there. Let's see, we have some comments in the audience. I get to the comments. I wanted to try one more thing. So we are testing 64 megabyte and I think they should work all correctly, because the mem test is indexing all of those, well, at least mostly anyway. So if there would be something, which I also had to do, right? So original NES code did not use all the address lines. However, most of you probably don't have this fancy. I heard also it's out of production. So apparently you can't, maybe not necessarily buy new stock of this 512 Mbit SDRAM, maybe the new max is 32 megabyte or something. So given that many people will most likely have another SDRAM on there, the crowdfunding, crowd supply stuff going live there maybe in a month or so is listed to have 32 megabyte and not 64 like we have. Lucky us. But the problem with this is, so we have for the addressing, you see here, we have 8 Mbit multiplied by 16 by 4 banks. And the problem with this is that the code right now would not work. If you have the same board with 32 megabyte, it would not allow to address the memory, because I guess at least we should probably double check. Let's maybe double check that before I change the code. Probably should actually, before we speculate again, and that would be 32. Wait a second, which did we open here? Wait a second, 32, 16, which, 32, 16. All right, so this would be 16, would this be 16M, 16? Probably, huh? Because if this has 4 banks, we would need to change the bank addressing a little bit, and I think, yeah, it should be, the question is how many banks does it have? Bank, yeah, so it has 4 mword by 16-bit by 4 banks. So given it also has 4 banks, which is what I expected actually, it will not work, because we use all address bits and the banks last, and given this addressing, we will miss one address bit there. So if you address this, you will not have, with this other integrated circuit, you will not have one continuous area of memory. However, I think we can simply change this by moving this, just moving the bank addressing a little bit lower. I think this should just work. At the RISC, all the SoC and the whole system should actually not care where the banks are addressed. So the bank addressing is this one. And I think if we move this address, so for example, if we want this to work with two smaller tiers, then we probably can make this 23 and 22 and move this like switch the bank earlier and use the highest addresses. Then of course you have still less memory, but at least you can still address it all continuously. So that would be 35, so that should be this ones here. And if we just compose them differently as 23, and if we just compose them here as, actually I wonder if you can type this slightly different, but basically taking 2 bits away here to 21, we have there 23, 21, and then adding here the high bits before that, so that we have like the highest rows are simply not there, which then the smaller have less rows there in there. So that would be 25, 24. A little bit, yeah, not sure if this is a common trick. I was just thinking about this earlier. Let's resynthesize and flash this while and then memory test this. Let's check once more. I don't think there is a typo, right? 25, 24, 23, 22, 21. That probably looks good. Let's see what we have in the comments. So welcome again, everyone. I hope you enjoyed this and learned something. Carlos heard that the Windows graphic interface is more fluid and fast than desktop environments. If it's right, did you think have something with X-Server? Well, X-Server is certainly not the most amazing. Yes, the X-Window graphics stack is totally outdated and not amazing. And more to this, to more videos. Also, yeah, I had already a previous video, 2D stuff, like line vector stuff, not isolated. Windows, the graphics stack is not, indeed maybe one of the better things probably in Windows. I'm so honest to admit, like, yeah, this X-Winding stuff. Well, certainly the X-Winding people know themselves that they for a decade already tried to get Wayland out of this is mostly what Wayland is for. Carlos asked, what's my opinion about desktop environments and VMs that we use here in Linux? Well, as you see, I don't need much. GNOME and KDE became way too big for me. I prefer much smaller code base. I basically run Blackbox because now I just need some Windows. Big Dice writes, 9 viewers right now. What you keep motivated making this long live streams so often? What's your purpose? Well, we have 50,000 views a month, and over the course of some days it gains some 200, hopefully soon 10,000 views. We will also soon continue with more stuff, but I need to do it anyway. If I want my own RISC-V system here, then this is for me just like you learn something. And also, given the state previous video, all the IT news and security stuff, we certainly need more educated people and not those people at all this OS and antivirus and Intel and bugs and stuff. And it is true, but you probably realized also we are not here after the monies. Given that we stream here highly technical and not that mainstream content, although thankfully we still gain subscribers each day, which is amazing. Thanks to everyone subscribing, sharing and liking and stuff. And over the years, of course, long term, this will be more. I have no doubt there. And yes, I'm fully aware I would have more subscribers if I will do more mainstream videos, which we also have done, and we will probably have to do a little bit more. But yeah, no problems there as long as other people buy our Don't Delay and Try Exact Scan, paperless scan software, OCR, PDF recompressing stuff, all there on the probably shameless shave self-promotion. And do this looks on the first glance okay. Let's run the full memory test. So yeah, Don't Delay, run, Try Exact Scan business software stuff here on our websites today. Yeah, no worries there. Thanks for worrying. You can also super chat, donate stuff like people sometimes do, and Patreon for all our Linux stuff, which also somehow, yeah, you do your data and then there are not so many open source updates anymore. But anyway, Memtest fails, that is not good. So much to changing. There's some bits around. That would be bit, which bit is it? Probably some bit we just moved around. So much to just changing some bits. 20, so bank 22, why would that not work? So should that not just work? 110 didn't change that. 24 address. 25, 24, 23, 22, 21, don't really quite see. I slightly wonder, I never tried this. Do you think Verilog supports something like that? But I guess not. Huh? Okay, so much to that. Try, I can just revert this anyway. This was just not really sure why this doesn't work. Unexpected, yeah, of course this doesn't work. Why would this not work? Strange. Anyway, did I even commit this previously? Always a good idea to commit this SDRAM. Was this fully? So address, okay, this was not yet committed as you see, because I added the last address line there just now. Really funny. I would think this shouldn't matter at all. Anyway, I will continue thinking. As soon as more people have the board, then we need to think about this. Otherwise, 23, 24, 25. If you spot a typo in there at home, playing along at home, let me know. Fun stuff. Let's see, everything is relative for the given feature set. It might be true since it has integration with graphic hardware, and it's definitely not the fastest. Everything has to start from somewhere. Pretty much no one watched us if we streamed. Those stuff is so cool, and we have success. Yeah, also. Again, not only, I certainly knew all the stuff in theory, but it's always something of knowing it in theory and knowing it by heart and really have done it, like knowing in theory how your car engine works and really repairing one. And also certainly it helps us for at work and our professional work at Exacode with our scanner reverse engineering and probably and all the other embedded project stuff. Designing hardware and RISC-V stuff. Who knows, maybe next year we are big in the RISC-V game. And also for our RSX P3 reverse engineering that I'm totally aware that plenty of thousands of people are waiting for. So knowing all this bit fiddling by heart certainly can only help with writing our microkernel, writing RSX NVIDIA stuff for the P3 and all this fun stuff in between. Electronics on the SDRAM core, Mr. The refresh time is actually set to be a bit faster than it really needs. The refresh timer. So there's the refresh pending. Wait a second. We have here plenty of comments. And all the stuff scrolled away. Carlos, Woman's preference, man is like its kernel hacker. Exactly, so how the refresh handles. How is the refresh handled with burst operations? Will it refresh prematurely if it's determined that a burst operation will take longer than the number of cycles left? Well, I thought all the non-prefetched rows are refreshed automatically. The specification list specifically you can stream out a whole page, so I would think that this stuff can handle, like somewhere it's written here, like burst, like full page, and serial data first row. It even says that full page operation is only possible using sequential burst type. Full page burst operation does not terminate once the burst length has been reached. At the end of the page, it will wrap at the start, address, and continue. In other words, unlike burst length 248, full page burst continues until it is terminated using another command. So I would think this stuff should auto refresh even if it continues bursting, I guess at least. But anyway, this is right now not really our problem. But especially as we have idle, we are not controlling the refresh anyway. So we are basically just telling this stuff like idle auto refresh, and it's cycling through its internal refresh logic anyway, so whatever, I guess it should work. But yeah, again, it makes more sense because if we only optimize this, I right now don't have you fancy video to show. It would of course be more amazing to have you have some video playing and some music playing and some game playing. So of course I will do all the features first. This stuff is stable now, at least at 83.33 or something megahertz, and more fine-tuning at the end of the year or whenever we feel like having too much time for this. Let's see, refresh, don't even know how to read chips behave in this scenario, would be fun to know on this SDRAM core. Pending, yeah, sounds easier to implement than having a bunch of state logic encounter. Things auto refreshes just when you drive RAS and low at the same time, so it only takes about 3 clock cycles, including some small delays. It could be optimized further, but the refresh pulse only needs to happen, say, once every 1004 DRAM clock cycles, so it usually minimum impact. Auto refresh just means SDRAM chip itself has an internal address counter which activates a whole row, and when it writes back, increments the counter. Just refresh whole array bank within 64 something would be. If it uses a frame buffer, you need to be careful that the refresh rate falls in H blank or V blank using blanking interval. So the video line takes around 8 milliseconds, 480p 60. Since the whole bank would need to be refreshed within interleaved between chips, SRAM buffer for each row. Hey, and this memory chip, yeah. So not really sure why this doesn't pass, honestly. Doesn't make the most sense to me. Strange stuff. Anyway, if you know why, just shuffling, because I would think for this chip it shouldn't have any kind of impact in which order we address this, as long as it's consistent here with our own addressing, obviously. It should not really matter, so not really sure. Anyway. 182 rows typical. So this is 64 mbit chip. Micron supplies Verilog models with timing information for those chips. So it have to refresh pulse once every 7-8 something visual blank. Micron seems to be de facto standard for models databases for some reason. Yeah, maybe they have the most quality tools and specification documentation. Usually those who provide the best tools to the developers usually becomes the de facto standard, or actually how does this work out with Windows? Or otherwise you bribe your customers to take it anyway. So if you get strange bugs, it can run on the gate level simulation, verify output from users in Icarus. So it might never written proper test benches. Yeah, so even in very later, you just emulate SDRAM and see. Yeah, so formal verification stuff coming soon because we want to set you good examples. Right now, this is good enough for us. Maybe I poke some of those FPGA gurus there, another, not to say geniuses, another day, or someone fixes this. Also, of course, we push this here to GitHub. The previous code is already there. So SDRAM V. So this is one higher address. Sorry, so this is, yeah, as you see here, was one less address. Previously 0 for the columns of the NES ZV. So this is just wire up 20 up all 25 bits in the SDRAM controller. Working, amazing stuff. Is there a reason it can't just request any word within the row and start with the so as soon as it goes off the chip, it will, I like to have time accurate SIMs. What they didn't know until recently is how you have to the burst access within a certain word boundary, the address within that boundary also wraps. It's wired, yes. So you have here some burst patterns depending on whether you configure interleaving and whatnot. So here are some tables of patterns. Oops, also pressed the wrong button now. So it would be burst. Also, I don't like some of those diagrams here are graphics. Which is super annoying. Actually, they're not even sharp. And certainly here, so there is like starting address, so this is just sequential burst addressing decimals here, but I'm not really sure if, yeah, so you can obviously configure sequential or interleaved, and 1, 2, 3, whatever, not looked into the details there. Here's actually some difference in that, but yeah, anyway, let's see. Could just request any arbitrary word and the chip would read the whole words from the row onto the buffer first. I'm not sure if it reads all. Probably doesn't read. Does it read at all? Not sure. Anyway. If so, you can fetch the critical word. Well, I think as far as this goes, I think you can use any starting address though with this bursting. As far as this, it's just even continuing. As you see, it's continuing with the correct sequential addressing here. I think this should indicate, probably doesn't. Anyway, is there interesting pin? What then do burst access from this point? And the interesting string pin saving done on the newer. There's an interesting pin saving done on the newer 128 megabyte SDRAM board on Mister. The DQAM and signals are tied to the upper address bits since they're only valid during different control pulses anyway. I would say this since the most common mode is for cache fetches, only the logic for that implemented in the reduced complexity plus CSN. I also really hate when but unlikely other signals, DDR, voodoo stuff like auto control timing calibration. Okay, today we have really many amazing comments there that you probably all want to read there. DDR an order of magnitude extra complexity, who will cores hooked up to something. DDR does voodoo stuff like auto current control and timing calibration and lots of different traces. Christian mess with training Broadcom processor, MIPS running DR was annoying enough. Do I want to know? Sync rollings must be calculated when you can just do constant. I think the rollings might be calculated where you can just do constant page mode burst, which in turn kind of refreshes the array anyway, assuming you're reading the whole thing. Most retro machines do refresh that way, so they use a large chunk of DRAM as a frame buffer actively feedback the data pane managed. Achieve unlimited length burst by issuing a burst for the next page exactly when the current burst ends. Don't they have a chance to debug this stuff without signal trap? Guess I found the PCB once. A point of underscore to indicate such a data sheet. Well, at least say the DQM for the byte addressing, they are indicated here as negative date data mask. This was DQM R. This is low and upper. DQM should be DQ. I mean, you see this is a bloody bitmap that is bloody unsharp. And so yeah, they have the lines here. So DQ LDQM don't have. Oh, wait a second. So they don't have. Well, maybe it's because a mask, and mask is like, oh, anyway, whatever. Maybe indeed slightly confusing. Anyway, so yeah, totally amazing for me anyway that this memory works, and certainly for me that it's 64 megabyte. That's certainly a whopping a lot for amazing. So yeah, something like StarCraft, SimCity here on this RISC-V. Fun stuff. So next SD card and then keyboard mouse, maybe importing other people's USB code, not yet sure. Certainly for the RX32.little with the icebreaker, some PS2 keyboard and mouse stuff to do. And then we always at the N signal name in Verilog, no, active low, reset N. Seems data sheet say DQM without even having a bar thingy. Yeah, maybe they assume mask is intentionally, like because they are masking it is, yeah, if high then mask, so maybe they actually take them as positive logic for masking, maybe. From the project runs full current CPU, sync, passive, something, 3D, GL, something, what, to run some 3 in this board with OpenGL or maybe full current. You mean in Verilog? Well, if you write your own GPU in Verilog, then you can run something. Otherwise, yeah, can't handle it when Verilog HTML, which has imported signals or an instantiation port, list which are active low and not made obvious here. Wouldn't like use up way too much logic, make sure full GFX API practical, I think. Yeah, so what I definitely want to do another time, but again, as already people ask what keeps us motivated, next videos will most likely be a little bit more mainstream, because mainstream, and otherwise I would love to implement on our VGA core here. Let's also run another mem test, because why not? Also, yeah, soon more user-friendly demos of showing something nice. And in our VGA core here of also probably I will probably rename this. So if you look for this file soon in the future, maybe I just rename this video, because certainly it doesn't have the most in common with VGA. So here I will most likely implement, at least for the RX32.big here on this ULX3S with this 84,000 logic cells or slices, some graphic acceleration, certainly bit BLT of copy of previous videos that we have done this on S3 and Cyrus and other vintage cards. And maybe in a year or this winter or something, if I'm feeling like it's depending on how busy we are with whatever projects, but maybe I even try to implement garage shading and texture mapping just for the fun of it, shouldn't be that complicated. Famous last words, but certainly not before. This is fully usable with 2D shooters, Pac-Man, and maybe even some small X-Wing versus TIE Fighter like demo. Useful demos first, and then fancy graphic acceleration another winter. Navarro, greetings to Davos. So sounds, are you always in Davos, or did you recently travel? So then, yeah, greetings to Davos. Not that far, actually. Very small subset of OpenGL or something. So yeah, if you speak about, but this is also the story for another live stream, if you speak subset, you need to think what. Certainly it makes no sense to implement GL on hardware. It's not like command level, so subset as subset of what, like this word voodoo of textured and shaded triangles, or what subset of what, but yeah, depending, we certainly get something and experiment it and see what. Usually with this kind of designs, this audio and video here, I usually for this kind of fun projects, I try to what is the easiest in hardware, not like defining some API, but like what we want to achieve, prototype it, and then see, okay, this is the most easiest way to do it. And yeah, and then, so yeah, if some guys run Crysis rendered by software on a Threadripper, yeah, okay, fine. So people are doing really many comments today. So yeah, Avidran Domer writes, DQAM isn't technical active flow because it's a mask. Yeah, that's what I said. Thanks for that. So yeah, most likely people also say Doom, so they already have Doom on an FPGA, but it runs really slow. Huh? Using a small CPU core though. So yeah, next we will maybe, well, next certainly something like Pac-Man Tetris, just for the fun of it. We have already video output. So on the hardware level, next is SD card, initially with its SPI mode for simplicity, and then keyboard and mouse, certainly for all the boards, and then maybe another weekend Doom. Was blown away with maniacs running Doom on the ESP32. We have come a long way here. Also come a long way with also open hardware and open source software synthesis tools. Certainly pretty amazing here, that what we can nowadays do here with all the yeah, benchmark all configs. Totally amazing. Toggle continues, is it? It doesn't even print it out. Fun fact. Switch to quad DDR, run the benchmark is 9. So cycles 9. Yeah, continues really slightly faster, run the benchmark again. Stress testing here our fine self-defined hardware logic. So yeah, most likely, yeah, also for this VGA, we need to increase here the code a little bit of supporting, now that we have so much plenty video memory, supporting here 8-bit color, full 8-bit color, and maybe even more. Let's see how much memory we can squeeze out of the internal block memory on the ESP4, and then let's generate some pretty graphics. And about chip relabeling. Okay, need to check chip relabeling, haven't changed it. So Ash said true, analyze true, something wrapping chips, unwrap, single basic cell chips, but they still keep, you think it would be the basic of selling chips, but stuff like even certain types of cardboard were banned from the clean rooms. Yeah, welcome everyone. I think the only subset of GL managed on the FPGA is flat shaded polys. Well, I would think something like the de-escalator of the S3 Verge previous video, where we programmed this low level. should be. The texture mapping should actually, well, the question is of course how fast. I think both should not be too bad. I mean, we have a full RISC-V core. We will see another. Well, basically, so the fun thing is with the FPGA hardware, we can each time we want to improve something like more frequency modulation stuff, like we just instantiated our stereo sound, making this support more waveforms and so on. It's just like, yeah, just a little bit of Verilog, and until it works, a little bit of guru meditation and probably better formal verification. Even the method for doing the dot product normal TC looks well. The ground shading is just fixed shading this stuff. So what you would do is you would do this on the CPU and submit a bunch of ground shaded triangles. So yeah, it's not doing the math. It's just like previous video. Delta value filling those anyway, but yeah, so your graphic API on the software stack would need to pre-process it and split this into a handful of vertices. Pretty nasty, and don't want active flow stuff, everyone and intended stuff. So yeah, I've also we have here also a little bit more stuff. So we have here git diff of, we touched probably VGA, not, did we touch VGA or maybe a little bit? What have I done here? Right, I can't commit this, I just brute force. I also need to clean this up so that this instantiates properly with Icebreaker versus ULX. What do we have in the ULX3S? Maybe some clock, probably, and yeah, also commit for no final ULX3S PLL mem and system frequency and SDRAM. How do we call this? So yeah, ULX, push this to GitHub there. And what else do we have here? Right, in some perspective of doing 3D. And so yeah, the problem is if we discuss all the comments here, then the stream always gets so long. Usually not in Davos, kind of, okay, amazing stuff, even school for amazing stuff. Connectivity mismanagement becomes worse in Germany. I'm here in no time. Yeah, know what you mean. Unfortunately, this political mismanagement is all over the world, not only in Germany or USA or UK. Problems all over the place. Probably best pro tip, vote for more clever politicians, preferable with an IQ over 50. And let's see, attempting to wrap brain around Sega Saturn polygon rendering. Yeah, also we will continue reverse engineering, so RSX stuff to come also theoretically. Also next microkernel. And yeah, so many projects, which is also, again, why I try to build this YouTube channel, to have a little bit of financial return here to do all the fun stuff, because also not only PS3, RSX and GMA Intel PulsePro Power VR. Most likely I look into the Dreamcast emulation and see if I can take some bits from there, especially for the old Kuro, maybe for some low-hanging initial implementation stuff. Let's see, what do they have here? Tried to do some N64 style poly rendering in Verilog years ago, implemented some of the MAME stuff. Did it to ground shading, but all the params were grabbed from actual games. Never found out why when we were drawing more complex models. Lack of pixel precision. Each pixel is subdivided by 4. Something DSP coprocessor. Really intrigued writing some audio graphic DSP stuff. J-Corner. Yeah, so the problem is I have so many different, so the problem is also twofold. Not only, I'm amazed how many 200 something views these videos sometimes get, FPGA, and how many people share, like, and subscribe, which is amazing. The issue is, of course, we have some other things to do, including this previous video, the sound card I built 20 years ago. I never used it because it didn't work. The external board I now use, which works, but I also have this ISA card. So this is DSP 64K, Motorola DSP. So also theoretically want to do something with this just for the sake of it and my fun and your education. So yeah, intrigued to writing some audio and video code, not only on PS3 and all this fun stuff, but certainly we need to find a good mix here to entertain and get people to share, like, and subscribe here for our digital self-reliance here on this channel. That's it probably here for today. Last comments. Avid randomer fact building, something like rendition Verity and FPGA would be cool. Yeah, also previous video, we have videos, right? I just purchased this for this fun. Rendition Verity is bloody complex, so with its MIPS-like core, what we could actually do is easily instantiate a second RISC-V core to do graphic stuff. Maybe we will do this. We will see possibilities endless. So we could actually have a main RISC-V core and an audio, like maybe reduced, like only 16 registers. Pico RV2 has support for this, 16 registers. Not really sure if GCC has support for this. Need to check, but just to keep the core a little bit smaller, and yeah, like maybe even more reduced Pico RV 32/16 on for audio video. Theoretically you could do this. This is also the fun of this, like designing your own systems and all this fun stuff. Custom instruction would be nice. Gain normal processor separate with 5 core would be like, yeah, like instructions. Like the problem is also, however, special instructions, often like floating point support stuff, easily take plenty of logic cells and slices. So yeah, we will see where we get. Right now we have plenty of logic left. We use in the meantime we have run here so much stuff. So the problem is it's not too far away actually. So we are right now using 5200 trellis slices. So this 12% of, actually not really sure what, because we have so maybe this is like 10,000. Do we have here some other total lots? So 7,000 of here's lots of this packaging, so 9% of this lots, and so 7,000 out of 80, nearly 84,000. However, they count here others of logic carry and so on. But here 9% or 11%, whatever, 12%. So plenty of room. Certainly we need to improve our FM synthesis for more waveforms and keyboard, mouse, USB, fun stuff. Maybe a larger, higher performance RISC-V core, and certainly ourselves some first level cache, but I'm repeating myself for those who tuned in last. That's it for today. Really now, I hope you enjoyed this. Still thinking how to do this comment discussions the most efficient, but anyway, again, if Louis Rossmann can stream a random garbage of his cats and armchair, it would be amazing if you share, like, and subscribe. Not that we need to resort to buying us a cat and live streaming cats and empty chairs for you to share, like, and subscribe. So would be amazing if you would do so without cats and without empty chairs for all those people to tune in. As usual, leave in the comments below what you found most interesting, what you would like to see more. More FPGA, more GPU, CPU, Linux, PS3, SGI, you name it. We have certainly, my list of YouTube stuff is already 25 videos long. So hope to see you soon for all this next videos and live streams to come.